Hi everyone, in this video I am going to teach you the green theory. From the fundamental theory of calculus I will start to reach the two forms of the green theory. Then I will solve as an example related to this, and we solve within software of MathMaple to represent better visualization of the example. The fundamental theory of calculus says that if we want to get the integral of derivative of a function f between segment A and B, the integral always will be equal to the antiderivative of this, which is f, and it's only depends on the terminal and the initial points of f over these segments. If we have f here and I want to get between, for example, this is the x-axis, which change from A to segment A and B, so the integral of always derivative of f, which derivative of f is actually will be tangent to f, always will be fb minus fa. I don't want to discuss here the fundamental theory, and just I want shortly to reach to the green theory. And after, when we want for the line integral, the fundamental theory change to this integral of gradient of f dot dr. This is dot product, and here we will see that gradient f is the form of f prime, which sits instead of f prime, and this is also depends on the initial and end point, terminal points of f. Here it is not the line segment, we have a curve over a space. For example, if I consider we have a space, or if I have a space here, and every curve C which I consider in this, if I want for from P0 to P1, and that the integral of the gradient of f. The gradient of f actually is a vector field, and enriched and sit instead of derivative of f. The gradient of f in every point has, but here if I consider the gradient of f, this is just depend on the scalar function of f in 2 point P0 and P1. And after I want here present the green theory, we have actually two forms of the green theory. First is circulation form, and the circulation form, and another is flux form of the green theory. Green theory says that if we have a region D, which is simply connected region with the boundary C, which is piecewise smooth, simple closed curve, and also always counterclockwise oriented, and we have a vector field f with component function p and q, which has a continuous partial derivative on d, then integral of dr, which is equal to integral of p dx plus q dy. Very simply, we can compute by double integral over the region d from q over e, derivative of q over e minus derivative of p over y times dA, which is equal to dx times dy. So better we, in order to understand what is this green theory says, if we go to line integral, if we have this region which ratio as of 3 points in this region influenced by the vector field, which shows as the blue color, and if you move over this boundary of the curve, you will see that the line integral always will be defined by integral of if you move along this curve as you influenced by the vector field, so this is a line integral is dot product with these displacements of the r. So if you move here counterclockwise, so here the dr is displacement, and also every particle here influenced by the vector field. For example, here in this direction I have the vector field F. When you move counterclockwise, so here has an angle theta. I suppose that is the theta. Let I write here. So moving over this, and here dr t displacement change, and also this is under the vector field F. So in this direction, if I consider this image, if here the angle is theta, so this vector image will be magnitude of F in cosine. This is the image of F over this direction of moving the particle, or you if you are on a boat. So this will be the work, for example, you done, it will be this multiply in displacement that we show as dr, or multiply in dr. This will be equal to the dot product of f and dr. So this is also the Green Theorem coming from the line integral. Now if we come back to this Green Theorem, we will see that here every point is under the vector field, and here the line integral of dot product of the vector field in the displacement, which is equal to p dx, because the dot product of f is p and q dot product by dr, dx and dy. So the dot product is p dE plus q dy. In the Green Theorem, very easy, we can compute this over the double integral of this region D, and the derivative of q over x minus derivative of p over y multiply in dA. dA is dE dot dy. Here we have this example. We want to compute the integral of x ln y dx over round D, and D is described as this region, x between 1 and 2 and y between x and x2. So here we have p dx. If we compare with the Green Theorem, which was round D, F dr, and F actually it was P and Q, so P and Q dot dr, which was equal to P dr. It means dr is derivative of R, which is dx and dy. So here is dx and dy, and dot of both will be equal to p dE plus q dy. And the Green Theorem say this will be equal to double integral over region D. From q we can get derivative over x minus we can get derivative of p over y dA. dA is dx times dy. So here we have here, which is p dx, and q actually is 0. So in this formula, p is x ln y, and q is 0. According to the Green Theorem, is equal to double integral over region D, and round q over x is 0, 0, and round p minus round p over y, which is equal to x times derivative of ln y is derivative of y over y. So it is 1 over y. So it is qx minus py times dA. dA is dx dy. So as x change between 1 and 2, so it's better we get first dy and then dx. So x change between 1 and 2. Here I can put 1, 2, and y change between ex and ex2. This will be equal to integrate, and from dy we can get the integral, which is equal to minus x ln y, and this change between ex2 and x. Again dx, that will be equal to integral 1 over 2. And then first we put exponential of x2 instead y, so ln of exponential of x2 is this one, minus will be positive, x times ln of exponential of x. Then we get integral in terms of x. So here ln of exponential of x2, exponential of x2 will be x2. So we have x2 times x is minus x3 plus x times ln of exponential will be x. X times x is x2 x. So then we can continue this integration. We get integral of minus x3 is minus 4 over x4 plus 1 over 3 x3. Change from 1 to, first we put 2, then 1. For 2 we will get minus 16 over 4 plus 2 times is 8 over 3 minus 1, which we get here. And if we compute this one, this is 7 over 3, so we will reach to minus 16 plus 1 is minus 7, 15 over 4 plus 8 minus 1 is 7 over 3. So we can use common denominator, which is 12. So here we have minus 15 times 3, which is 45, plus 7 times 4 is 28. So minus 45 plus 28 over 12. If we decrease 8 from this is minus 17 over 12. So we get here, compute this integral, which will be equal to minus 17 over 12. And I want actually use the Maple software also and see how we can compute this example within the Maple software. In this video, I want to solve that question by Maple software. So in order to visualize better, let's plot the function with this. Let's use this sign, and it plots. I will the shade between. So to illustrate the region D, I use the shade between. The region actually is y is equal to e exponential of x2 and x, and exponential of x2, y change between 2 and x from 1 till 2. If I run this program, I enter and we will see the region D, but I want to keep it and after to show, so I put this name as A inside the A. And now I want to show the vector field. The vector field was defined by x times ln y according to that example. So I should write the field plot of x. Let I put the vector field. Vector field actually have two, p and q. P was defined by x time ln of y, and q which was 0. This between x equal to, here x is between 1 and 2. Here again I will write between 1 and 2, or maybe between -1 and 2, or -2 to 2. And the y will be equal to y here, as the ln y, the domain for this will be positive. So y I write 0 till anything we want, for example 15. Let I put b, this name. If I run this, here it is the vector field, and here it is the region, but the region under this vector field. So let I display in one diagram. So I use the program of display between two occludes. This name was A, shadow or region, and this name for the vector field was B. Let I don't run here and run both in same. So I put two dots here. Like the same column I change to this. Now I will run this one, and you see that we have a region in R2 which under the vector field, and the vector field for any vector we have the magnitude and also the direction, which here we can use the color change or also everything. For example, if I put green color, it will be this one. Now we have this and we want to get the integral and see whether our answer is correct or no, just we check. So we want to get the integral. So as the students before used, I used the with student calculus variate with student plus multivariate with student multivariate calculus. I want to integral, that is use multi-int. Multi-int when we want to get the integral of some things over a region which we want. So here I will put from which terms I want to get a multi-integral. So multi-integral we want to get from the round q over x minus round p over y, which before we compute as minus x over y. This we want to get integral according to Green's theory, and then over between y over the region which y is equal to exponential of x, and y change from this one to point exponential of x2, and x change from 1 till 2. So now we can compute something wrong that with a student. Sorry, I missed A here. Sorry, I was missed just here. We get the error that we variate. Okay, I missed A here. Multivariate, then we can run. -7, which before we calculate. So we get the same answer we solved in this question. Thank you for your attention for this video. Please subscribe to my channel if you're interested to get more video from the teaching these subjects. Thank you very much.